Welcome to Scully Unclassified. I'm Scully. I've been a software developer and architect for more than 20 years, and I created this channel to develop your skills as an embedded software engineer with a focus on aerospace. Today's topic, bits, bytes, and digital computing. Before I get into digital computing and start talking about binary numbers, bits, and bytes, I wanted to first talk about the difference between things that are analog and the things that are digital. So for an analog system, it's continuous. So if you imagine like a sine wave, or a voltage that could be going up and down, or even an analog record, where you have a groove physically scratched into the vinyl, and then that analog signal is the needle just moving along that groove. An analog clock has a minute hand, an hour hand, a second hand. They're constantly in motion. There's no one discrete moment. They are a particular value. For example, 6 o'clock, you have the hour hand pointing at 6, you have the minute hand pointing at 12, but that's always constantly in motion. When is it exactly 6 o'clock is harder to define. A lot of analog systems will use gears and pulleys. So for example, if you open up the back of a analog style clock, you would have clockwork, tons of gears and springs to get that analog system working in the correct time. When you think of digital things, they are a particular number. So you don't have a smooth, say, sine wave, you would have steps. So at that particular time, the value is at a particular number. A digital clock will say 6 o'clock, 0600. It is a discrete, fixed number, not an analog clock that's constantly in motion. You'd also consider a light switch, a digital system, assuming it doesn't have a dimmer. So if you do have a dimmer that adjusts the current going to the light bulb, that's an analog system. It isn't discrete on, discrete off, but if a switch, you'd flip it on and off. So when we talk about digital computers versus analog ones, if you go back to 1945, the vehicles in aerospace, planes, torpedoes, missiles, were all flown with analog computing. So with the analog computing, if you wanted to do something like adjust a value, or you wanted to multiply something, or multiply a particular value coming off a sensor, you just run it through a series of gears. So you had gears of different sizes, you could do multiplications or downsampling, and you would have sensors like a spinning gyroscope connected through those gears and pulleys to an effector. So a fin may be on the missile or on the plane, so that as that sensor moved or provided feedback, it provided analog feedback, either in movement or a voltage or current that changed. That analog system had physical components, mechanical components, that would then fly the vehicle, and you'd have direct connections physically between sensors like a gyroscope that would maintain stable, and a fin that would move to adjust the flight of the aircraft. We're talking about digital computing. So now there's a computer in the middle, a flight computer, let's call it, where the sensor still, if you have a gyroscope's itself an analog system, but you'd have a little computer in there that would digitize those readings. So instead of getting a physical movement or a voltage coming off it that could vary over a particular range, now you have a discrete number coming out, and that's encoded in binary, in ones and zeros, and I'll talk about that for a second. That'll go to a digital computer. That computer is going to then run its algorithms at a particular rate and send out a new set of digital signals or messages over a computer network to the effector. So you might have another little computer on the fin itself, and then it's moving the fin based on those digital commands. So let's talk about binary. So you may hear binary code. Binary just means 2, like bicycle has 2 wheels. So binary could be either on or off. So it could be 0 or 1. So if there's voltage on the line, it's 1. If there's no voltage, it's 0. And if you wanted to send a signal to somebody, you could give them ones and zeros by closing the circuit, opening the circuit. So for that particular line, you can have 2 different values. You could have a 0 or you could have 1. Now going into bytes, so a bit is just one line on there, 0 or 1. A byte is a grouping of 8 of them. And often you'll see things counted in bytes because it's a popular popular byte width. Sometimes you'll see 4 bits called a nibble, but that isn't really too useful. And if you go into the history of computing, you might find different byte widths. But standard now, 8 bits to a byte. And you can see that you can, if you have 8 bits to work with, each one could be a 0 or a 1. So you have all combinations from all the switches are off or all zeros to all the switches are on and any combination of them. So binary you could write as just zeros and ones, but it'll get pretty long. So if you have 8 bits to write and you had 8 ones or 8 zeros, it gets pretty difficult to capture those things. You can write them in decimal or base 10. That's our regular number system that we use. I have 0 through 9 is the digits and 10 for 10. Because bytes are 8 bits long, it's often good to write a value that fits within those bits. So if you want to write a value that's within 8 bits or within a byte, you don't have to write out 8 zeros and 1 all the time. Doing the conversion to base 10 can become a bit of a pain. And you really want to capture what values are within those 8 bits. That's where hexadecimal comes in. So hexadecimal just means 16. So you have like a hexagon, has 6 sides, hexadecimal, 16. So you can have 16 different values with 4 bits. So if you have 4 different switches, the total number of combinations you can have for those switches, either they're all being on, all being off. You have 16 discrete values, 16 discrete binary values you could have for those. If you were to have everything off, that would be one particular value. It would represent 0. And if you were to flip the first switch, you'd have 0, 0, 1. That's 1 in both decimal and hexadecimal. If you were to add 1 to this now, in binary, 1 plus 1 equals 10. Or 1 plus 1 equals 1, 0. So much like if you carry a 1, so if you have a 1 there, and you add another 1 to it, there's not a third space or a third digit. All the digits are 0 and 1. So then you carry over the 1. So now in binary, 0, 0, 1, 0 is 2. So you add 0, you added 1, you flip the first switch. Add another 1 to that. You carry over, so you flip that first switch back to 0. And then you switch up on the next switch over. Add 1 more for binary or hexadecimal, for binary 0, 0, 1, 1. Decimal and hexadecimal. Add 1 more, now you have a carry again. So 0, 1, 0, 0 is 4. You add 1, that's going to have a carry over to the next slot. That was also a 1. Adding 1 to that, you have carry over again, and now 0, 1, 0, 0 is 4. Add 1 more is easy, because the least significant space, it was already 0, so you just add 1 to it. Then you have a carryover, adding up to 6. 7 is 0, 1, 1, 1. And we add 1 more now to 8. You'll have a cascading carry from the least significant bit, which you'll end up with 1, 0, 0, 0, and that represents 8. Add 1 more is easy since it was already 0 in the ones place. Going to now decimal 10 or hexadecimal A. So hexadecimal is 16 values that you could have within a 4-bit code, 4-bit binary code. So while decimal numbers go to 0 through 9, hexadecimal numbers or hexadecimal digits are going to go from 0 to F. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. So while 1010 represents 10 in decimal, and we saw that because we added it up one at a time, starting from 0. It's hexadecimal A, because within that one hexadecimal digit, we want to capture all 4 bits. So we would write 1010 as hexadecimal A. Adding another one to it, we'll go to hexadecimal B, which is decimal 11. 1011. Hexadecimal of C, decimal of 12, 1100. Adding one more, 13 is D. Now we have 1110 for 14 decimal, hexadecimal E. And then all the switches on, 1111 is 15. We added it all the way from 0, and that's hexadecimal F. So if you see a hexadecimal of F, that every bit is 1. You'll notice as well as we're counting through, if we only had one bit set, it would be a power of 2. So that for each switch you might add, you're doubling the number of values you can capture within that number of bits. So for example, if you just had one bit to capture, you'd have 2 to the 0, or 1. If you had 2 bits, or the 2 to the first, for 0010, you have 2 to the first, or 2. If you were to have the next bit over, where you have 0100, now you have 2 to the second power, and the next bit up, you'd have 2 to the third power. So you notice that if just one bit is set, it's 2 to a particular power, so 2 to the 01, 2 to the first 2, third bit over, 2 to the second, or 4, fourth bit over, 2 to the third, or 8. And if you want to do a conversion between binary and decimal, each of those values that are set could be added up. So for example, if you had 0011, you'd have 2 to the first plus 2 to the 0, or 3. If you found this content useful, please like and subscribe. I appreciate hearing from you and would like to hear what topics you'd like covered in the comment section below, and I'll see you next time. Thank you.